Hello all, we are going to begin with transfer function limitations. Transfer function equals output of S divided by input of S at zero shell conditions. For the conventional control theory, which is applicable for single input, single output system, SI stands for single input and SO stands for single output. The system must be linear and time invariant. For the modern control theory, which is applicable to multi-input, multi-output systems, linear or non-linear systems, time variant or time invariant, which is more general than the conventional control theory. Now we will see the state space representation of the system. We will begin with an example for a mechanical system which is composed of a mass, a spring and damper with an input force U of t, and the output is a displacement Y of t. First of all, we write the system equation, which is m x double dot m times the displacement double dot, the second derivative of displacement, which is the acceleration, plus by dot plus ky equals the input, which is u of t. The system is a second order system. Since the equation is a second order differential equation, this means that the system involves two integrators. We will need two integrators for this system. We will define the system states. The first state will be y of t, which we will make it x1, the state x1, and we make the second state x2 y dot. Then we will have x1 equals y of t and x2 equal y dot of t. Therefore x1 dot will be equal to x2. x1 dot equals x2. We will substitute in the differential equation with x double dot by x2 dot, x dot by x2, and y equals x1. Then we divide all the equation by m, and the terms with x2 and x1 will be turned to the second to the right side. We will have x2 dot equals negative b over m y dot, or negative b over m x2 minus k over m x1 with the negative signs as we transfer them to the right side, plus 1 over m times u as we divide all the equation by lm. Therefore we have x2 dot equals negative b over m x2 minus k over m x1 plus 1 over m times u, and the output is the first state x1 of t. We can write these equations in the matrix form. x1 dot equals x2. Therefore the A matrix, the coefficient of x1 is 0 and the coefficient of x2 is 1. For x2 dot equals negative k over m x1 and negative b over m times x2, and for the input u is multiplied by 1 over m. For the output y equals x1, 1 times x1 and 0 times x2. The general form of the state space equation is x dot equals ax plus bu and y equals cx. Those are the two equations, the state derivative equation and the output equation. This is a recap for the previous equation for the output and the states. x1 dot equals 0 times x1 and 1 times x2, and for u We don't have a coefficient for u for x1 dot, then 0 times u of t. x2 dot equals negative k over m times x1 and negative v over m times x2. And for the u, we have 1 over m times u. Y of t equals 1 times x1 and 0 times x2. Then we will see an example for the electrical system. We have an electric circuit with V input, resistance, inductance, capacitance, and the output is across the capacitance, the voltage across capacitance. We will write Kirchhoff voltage law for this circuit. V input equals R times I plus L di by dt, the voltage across the coil, which is L di by dt, and for the voltage of capacitor, which is Vc of t, which is the output of the circuit. We can write the current equation as a function of the voltage across the capacitor as I equals C dV by dt. And therefore, we can substitute by di by dt, which we will take as the first state as x1 dot. Therefore, I equals x1 of t is the first state. Therefore, di by dt equals x1 dot. di by dt equals x1 dot. x1 dot. Therefore, L di by dt, we take di by dt as x1 dot and divide all the equation by L. Negative r over L times I, which is x1, and negative 1 over L times x2, which is Vc taken as the second state. Vc equals x2. VL is the Vc is x2. Vc is the second state. Therefore, Vc equals x2 plus 1 over L times V input, which is the input. For the current of the capacitor, dV by dt equals 1 over C times I, or I equals C dV by dt. I equals C dV by dt. Therefore, dV by dt equals 1 over C times I. I is the first state x1 and Vc is the second state x2 with derivative. Therefore, it will be x2 dot 1 over C times x1. And the output y equal Vc, which is x2. x1 dot equals negative r over L times x1 and negative 1 over L times x2 for x, and the coefficient of u is 1 over L. x2 dot equals 1 over C times x1 and 0 times x2 and 0 times u. For the output, which is the second state or Vc, then the coefficients are 0 times x1 and 1 times x2. We want now to see the state space modeling as general equations. The general equations is x dot equals ax plus bu and y equals cx plus du. X is the state vectors, the states vector, and the A is n time by n rows and n columns system matrix. B is the input matrix, which is multiplied by the input u, which is n by p. P is the size of the input, u is the input vector, y is the output vector, and C is the output matrix, which combines the states to obtain the output. D is the feed forward matrix, which we are feeding forward the input to the output. Now we will see the canonical forms of the state space models. Each of these canonical forms has a specific advantages which makes it convenient for use in particular design techniques. Each one is used for a specific design technique. The state space models that we will see is the phase variable canonical form, then we will see the controllable form, then we will see the observable form, and last but not least the diagonal canonical form, which is we will see the Jordan canonical form. An interesting note that the dynamic properties of the system remains unchanged whichever the type of representation is used. This means that the dynamics of the system does not depend on the type of the canonical form you are using, it only depends on the dynamics of the system itself. First, we will see the phase variable canonical form. Obtain the state equations in phase variable form for the following differential equation. We will now obtain the phase variable form for the differential equation given in this equation. We will take the system states as follows. The first state x1, which is y, and x2 is dy by dt, x3 is d2y by dt square, and for the last one, which will be x3 dot, which is the derivative of x3. We have a third order differential equation. Then we will have three states, x1, x2, x3. The last state, or the last, the higher order of the derivative is the last state derivative. Therefore, we have x1 equal y, x2 equal y dot, and x3 equals y double dot. Therefore, x2 equals x1 dot, and our x1 dot equals x2, and x2 dot equals x3. For the last equation, we obtain from the differential equation, we divide all the equation by 2, and we will take all the states to the right side. Then we have negative 4x1, which we divide 8y or 8x1 by 2 and taking it to the right side, negative 4x1, negative 3x2, negative 2x3 plus 5u as we divide all the equation by 2. Therefore, the phase canonical variable canonical form will be x1 dot equals x1 dot, x1 dot equals x2. The coefficient of x1 is 0 and the coefficient of x3 is 0, and for the coefficient of u equals 0. x2 dot equals x2 dot equals x3. Then we have 1 at the coefficient of x3 and zeros for x1 and x2, also 0 for u. x3 dot equals negative 4x1, negative 3x2, negative 2x3, and the coefficient of u is 5. For y equals x1 and zeros times x2 and x3. State space representation, we have the nth order differential equation, y derivative number n plus a1 y to the derivative n minus 1 plus an minus 1 y dot plus an y equals b naught u power n plus b1 u power n minus 1 plus until bn minus 1 u dot plus bn u. U is the input and y is the output. The equation can be written as follows. We take the Laplace transform. The Laplace transform of the nth derivative is x s power n times y of s, a1 times s power n minus 1, and an minus 1 times s, an times y equals b naught s power n times u plus b1 s power n minus 1 times u plus bn minus 1 times s times u plus bn times u. We can represent this state space representation of the system defined by the above equation in the controllable canonical form and observable canonical form as follows. We begin by the controllable canonical form. For the controllable canonical form, we will take all the coefficients of the denominator from right to left, from an to a1, with opposite sign as the last row for the matrix A. Negative an, negative an minus 1, negative an minus 2, until negative a1. For the first column, it will be all zeros, and the rest of the matrix is an identity matrix. Once more, we will take all the coefficients of the denominator from the right to the left with the opposite sign, negative an minus 1, negative an minus 2, until negative a1. The first column is all zeros. The rest of the first column is all zeros. And the remaining of the A matrix is an identity matrix. For the U or the B matrix multiplied by U, all zeros and the last one is 1. All zeros and the last row is equal to 1. For the Y matrix, we will take the coefficients of the numerator from the right to the left until b1, from bn to b1, bn minus 1 until b1 times system states, plus the last one b naught is multiplied by u, plus b naught times u. Once more again, we'll take the numerator coefficients from right to left with the same sign, bn minus 1 until b1, and for the u we multiply it by b naught. Let's see an example. Controllable canonical form. Find the controllable canonical form for the given transfer function. S plus 3 divided by s squared plus 3s plus 2. We will take the denominator coefficient with opposite sign from right to left, negative 2, negative 3. It's second order system, then the matrix is 2 by 2. 2 rows, 2 columns. For the first row, first column will be 0, and the first row, second column will be 1. 1 representing the identity matrix, and this is the 0 above the row we have already taken into consideration. For the U, all zeros and last row equals 1. For the Y equation, the output equation, we will take coefficients for the numerator in the C matrix from right to left, 3, 1, and no coefficient. We take the coefficient until s power 1, 3, 1 times x1, x2. And for the coefficient of u, there is no coefficient of s squared in this equation, then the coefficient of u equals 0. Now we will see the observable canonical form. For the observable canonical form, we will take the last column as the coefficients of the denominator from the right to the left with opposite sign. The last column in the A matrix will be the coefficients of the denominator with opposite sign from right to left, from an until a1, negative an minus 1 until a1. For the remaining of the first row will be zeros. For the remaining part of the matrix will be an identity matrix. Once more again, we will take the coefficients of the denominator with opposite sign as the last column in the A matrix with opposite sign, from negative an to negative a1, negative an until negative a1. For the rest of first row will be all zeros. For the remaining part of the matrix A will be an identity matrix. Now we will see the B matrix. Coefficient of U will be the coefficient of the numerator. I'm sorry, coefficient of numerator from right to left, from Bn until B1. Bn minus 1 until B1. Then we will see the coefficient of Y. All zeros, the last one is 1 times xn, and for the coefficient of U is the remaining coefficient in the numerator, which is B naught. This is the coefficient of U in the Y matrix, B naught times U. Let's see an example for the controllable and observable canonical forms. Controllable canonical form will take the coefficient of the denominator from right to left with opposite sign, -3, -1, and -2 until coefficient of s square, as this is a third order system. For the coefficient of U, all zeros, and the last one is 1. For the coefficients of the C matrix, we will take the numerator from right to left with the same sign, 3, 3, and coefficient of s square is equal to 0, 3, 3, 0. Now we will see the observable canonical form. For the observable canonical form, we will take the coefficients of the denominator with opposite sign as the last column in the A matrix. The last column in the A matrix. And for the U, this is not right. -2, -1, and -3. The last one is -3. For the rest of the first row is zeros, and for the rest of the matrix will be identity matrix 1, 0, 0, 1. For the coefficients of U will be the coefficients of the numerator 3, 3, 0, which is 3, 3, 0. Bn minus 1, 3, 3, 0. For the Y equals 0, 0, 1, 0, 0, and 1. And for the U matrix, 3, 3, and 0. Now we'll see the diagonal canonical form. We have the transfer function in this form where the denominator is factorized s plus pool 1, s plus pool 2, and until s plus pool number n. We will get the partial fractions b naught plus c1 over s plus pool 1 plus c2 over s plus pool 2 plus until cn over s plus pool number n. This is Pn. For the E matrix, it will be a diagonal with all the poles with negative sign, and above the diagonal is zeros, and the part downwards the diagonal is zeros. For the U, coefficients of B equals all ones, and for the coefficient of Y, the C matrix equals C1, C2 until Cn times the system states, and for the U we have B naught times U. The last one is B naught plus times U. Now we will see an example. S plus 3 divided by S squared plus 3S plus 2. We factorize the denominator to S plus 1 times S plus 2, and then we get the partial fractions. The first partial fraction denominator is S plus 1. We cover S plus 1 and substitute with S equals -1, -1 plus 3, divided by negative 1 plus 2. This is 2 divided by 1 equals 2. And for the second partial fraction, we will cover s plus 2 and substitute by s equals negative 2. Therefore, negative 2 plus 3 divided by negative 2 plus 1, which will be 1 divided by negative 1 equals negative 1. We now obtain the partial fractions. Then we will take the opposite sign of the poles, negative 1, negative 2, and above the diagonal 0 and below the diagonal zeros. For the u, coefficients of b, all 1s. For the y, we have the coefficients as the numerator of the partial fractions, 2 and negative 1. We don't have a constant added here, then b naught equals 0, which is multiplied by the u. Now we will see the Jordan canonical form, where we have multiple pole s plus 1 power 3. This will get us a three partial fractions for s plus 1, which is c1 over s plus 1 power 3, and c2 over s plus 1 power 2, and c3 over s1 plus p1. And for the rest, sc4 over s plus 2 until cn over s plus pool number n. As the diagonal form we have seen in the previous slide, we will put negative p1, negative p1, negative p1 as we have a repeated pool, which is p1 3 times. The rest under these three pools is zeros, and above them we have 1 and 1 and 0. This is a small difference from the last one. The right side to this part is all zeros, and the bottom of this part is all zeros. Then we put the rest of the poles, which are P2 or P4. We can make it P4, pool number 4, as 1 is repeated 3 times. 1, 2, 3. This will be 4, negative P4 until Pn. For the U coefficients of the B matrix, first 2 equals zeros and the rest equals 1s. For the Y matrix, we have the coefficients of the partial fractions C1, C2 until Cn. And for the part of U is B naught times U. Now we will see how to convert state space to a transfer function. We have the state equations x dot equals ax plus bu and y equals cx plus du. Now we have y equals cx plus du, taking the Laplace transform of equations 1 and 2. Laplace of derivative x dot equals sx of s plus ax of s plus b times u. Y of t, we will have y of s equals cx plus du. Then we will substitute, we will take a x of s to the left side. We have si minus la times x of s. We take x of s as common factor equals b times u. Then we will get x of s by multiplying both sides from the left side by si minus la inverse. We will have x of s equal si minus la inverse times b times u. We will substitute equation 5 in equation 4. Then we have x of s will be c times x equals si minus la inverse times b times u plus d times u. Now we will take u of s as common factor. Then we have c times si minus la inverse times b plus d. Now we can get the transfer function. The output divided by the input will be c times si minus la inverse times b plus D. Let's see an example. Convert the following state space model to transfer function. Take k equals 3, b equals 1, and m equals 10. We have the equations we have proved in the first beginning of this lecture. 0, 1, negative k over m, negative b over m times x and v, which is the second state, and 0, 1 over m times the force over the input. This is the input. Y equals 0 times x1 and 1 times x2, which is the velocity. Now we will substitute by k equals 3 and m equals 10 and b equals 1. We have the coefficients of the matrix as we substitute by k and m and b. Now we will extract the E matrix. 0, 1, negative 3 over 10, negative 1 over 10, b 0 and 1 over 10, c 0 and 1, d equals 0. Now we have to calculate the equation C times Si minus La inverse times B plus D. We will have Si S0 0S minus the A matrix 0 1 negative 3 over 10 negative 1 over 10 all inverse times the C from the left and times B from the right. Now we will subtract each element by element. S minus 0 equals S. 0 minus 1 negative 1. 0 minus 3 over 10 equals 3 over 10. S minus 1 over 10 equals S plus 1 over 10. All inverse times 0 1 from the left and 0 and 1 over 10 from the right. We will get the inverse of this matrix. The inverse of this matrix is equals to 1 over the determinant, which is S times S plus 10 with a positive sign, and with negative sign, negative 1 times 3 over 10, which is negative times negative equal positive. S times S plus 1 over 10 plus 3 over 10. This is the determinant, 1 divided by the determinant. Now we will get the adjoint matrix. For the adjoint matrix, we will take S in the place of S plus 10 and S plus 10 in the place of S. Then we will have S plus 1 over 10 and this will be S. And we change the signs of the other two elements. Negative 1 will be 1 and 3 over 10 will be negative 3 over 10. Now we will multiply this matrix by this vector. 0 times S plus 1 over 10 equals 0. 1 times negative 3 over 10 equals negative 3 over 10. Then we multiply 0 times 1 equals 0. And 1 times S equals S. Then we multiply negative 3 over 10 by 0 equals 0 and S times 1 over 10 equals S over 10. Now we will multiply the denominator by 10. Then we will have S times S plus 1 over 10 plus 3 over 10 times 10. Then we will multiply S 10 times 3 over 10, which will be 3. And 10 times S plus 1 over 10, which will be 10S plus 1. Another example which we will see, obtain the transfer function for this state space model. This is the E matrix, and this is the B matrix, and this is the C matrix. We will obtain the transfer function as 10 times S squared plus 3S plus 2 and divided by S cubed plus 3S squared plus 2S plus 1. Thank you for now, and see you again in the next part of this lecture.